Self-driving cars are becoming a current-day reality. However, there are many small features today in current vehicles that help aid a driver. Many of these same features that may help self-driving cars in the future are actually implemented in current vehicles today. For example, my current car uses a camera mounted up here for various computer-aided signals. One of these is the ability for it to capture and recognize speed limit signs and then display them on the dash. This gave me an idea for a potential fun project. I decided to dig a little deeper into how a vehicle could actually accomplish this task. This is the speed limit detector, or SLD for short. Might have to work on that one. Anyway, it's rather simple in its perceived functionality, so let's walk through how it works. I'm going to hold up this printed speed limit sign and walk in front of the device to simulate a car driving past the sign. As you can see, within seconds, the device will capture the sign and then display the result on these 7-segment displays. This dot in the middle is actually not a decimal point. It's actually used to indicate whether or not the device has successfully captured a speed limit sign. Once it's captured, it has to process that image, and that dot displays whether or not an image is being processed. It seems rather simple on the surface, but underneath this black box is a much more complicated underlying system. But first, let's dive into the electronic/physical aspect of this project. I'll let my partner Clay here outline this.
The Raspberry Pi was a perfect device for this sort of project. It allows for more complex computer processing, but also for electronic extendability through its GPIO pins. We decided to use two 7-segment displays to display the speed limit. I was in charge of wiring the output of the Raspberry Pi to these displays. Each segment of the displays acts like its own LED, although with a common ground. This means that each GPIO output pin corresponds to one segment of the display, with each display only needing one ground returning to the Pi. Each segment also required a 220 ohm resistor to limit the current to protect the GPIO pins.
While Clay got this electronic aspect functioning, I was working hard on the algorithm for the camera input. So let's see what's going on here. So I'm using multi-threading to make this work. So we have the main thread here, which takes the camera input and uses something called a hair cascade to detect the speed limit signs. Not the values of the signs, but just the signs themselves to see if there even is a sign in the image. Then, if a sign is detected, we'll store these images in a queue. And then, on a separate thread, we will take the images in the queue, and if there are any, then we'll perform text recognition using something called Pi Tesseract. This hair cascade algorithm over here will actually crop out the speed limit sign before storing it into the queue. So we're just performing text recognition on the cropped out sign of the camera input frame. Then we'll see if there's any text in the image, and if there is, then we'll see what the value of that text is and then send the output to be displayed on the 7-segment displays. So the reason for different threads is that because the Raspberry Pi is fairly low powered, all this processing takes quite a bit of time. So by splitting it up into two separate threads, what we're able to do is still continue to process frames and take their input while still being able to perform text recognition in the background. That's why when you hold up a speed limit sign, the little dot appears on the 7-segment displays in order to let you know that this separate thread is processing in the background. But while that's processing, we still want to make sure that we don't miss out on any extra frames that might be helpful. So we still collect them and store them into the queue while there's processing going on in the background. Next, we'll look at the actual code itself. So here we have the 7-segment display here, along with all the labels. We're just going to kind of run through this. These are some of the variables to help set up these 7-segment displays. And here's our cascade classifier. So I'm using something called a hair cascade, which is a machine learning trained model to try and classify certain objects. And usually it's used for face recognition, but it can be used for any kind of purpose. And I actually found this online. Someone actually had trained a hair cascade to detect speed limit signs. So I was able to just download this XML file and be able to use it to tell me where a speed limit sign is in a particular image. So then when I set up the webcam and go down to the main loop down here, we're going to get each frame here, read the camera, convert it to grayscale, and then we'll go ahead and use that cascade to detect our speed limit signs. And so then we get a list of signs, which usually there's only one, so we loop through them, and then we get the position of it, and then crop out the image, and then I'm using a function here that I found online as well, which will help me correct skewed text. So if the speed limit sign is a little bit tilted to one side, I'm able to kind of correct that as best as this algorithm can, and I'll go ahead and add that to our queue here. So that's pretty much everything that's happening on the main thread. But once something is added to the queue, we go up here to our detect text thread. So this is running in a separate thread, so it's in a continuous loop, and it's going to detect if there's anything in the queue. Once there's something in the queue, it'll configure PyTesseract, only detecting digits, because we don't want to actually get the text that says speed limit, we only want to get the numbers on the sign. Then we perform the actual operation and get the text. And then we just see if any of these numbers are within the text. Telling us if these numbers are on the sign, indicating that that's what the sign says. We set a variable for that, we can print that value out, and then once the actual value is set, so we actually display that value on the main thread. It's just going to continuously update the 7-segment display with the limit variable, which is set on the separate thread. And then we display that number with this function here, display num, so we can clear the display, which is over here, and it's just going through the GPIO pins, setting them all to low, doing some formatting things to make sure if it's a single digit number that we have a 0 in front, and things like that, and then looping through the GPIO pins, setting them all up to display the correct number. And so that's pretty much the whole setup here. There's quite a lot of moving parts, but it all works out in the end to create something that actually functions correctly. Overall, this project was a great exercise in many aspects of computing, such as computer vision, image processing, multi-threading, interfacing displays, and the interaction between all these various elements. Although it may not work perfectly in the end, such as in the real world with an actual vehicle, the idea still remains the same, and through this project, it helps to not only understand but also appreciate the complexities of the technologically advanced world we live in today.